Here we are going to solve the few problems related to the moment. In this problem, uh, we are going to use the principle of equilibrium, in which we can say left moment is equal to the right moment, or clockwise moment equal to the anti-clockwise moment. So you can see in the diagram there is a uh, pi bottle which is here, and one weight which is 0.6 meter from the pi bottle, and this is rotating in this directions, and this is rotating in this directions, and other way this is rotating in other direction, and you can say this is the clockwise, and this is the anti-clockwise. Okay, what is the left moment? Left moment is the anti-clockwise moment. Anti-clockwise moment, or you can say left moment, equals to, we have two weight. One is 7.6 Newton and other is 3.3 Newton. And so we have to be more careful how far this, the distance, right? So it's gonna be 7.6 into how far the distance is from the pivotal from here to here. How far it is? It's 0.6 0.06 meter, and another weight is how far from here. This is 0.06 from here, and 0.04 means it's gonna be 3.3 Newton into 0.04 plus 0.06. That equals to the 7.6 into 0.06 plus 3.3 into 0.1. This is the left moment. What is right? Right moment. Right moment, or you can say clockwise moment. Clockwise moment is equal to P into, we have to calculate that 0.08. So in this case, both are equal. So our equation will be P right moment equals to 0.08 because 7.6 0.06 plus 0.33. So P gonna be 9.975 Newton. So we are calculating the total force P, so that the clockwise momentum equal to the anti-clockwise moment. Okay. In another problem, it's a wheelbarrow problem. Wheelbarrow, it's carry the load in the wheelbarrow. What happened? And this is the pivotal. Here is this one point. Here's the wheel. There's the pivotal, and the load. You are applying the force in the up direction, right? This is the up direction, which is the anti-clockwise direction, and the weight, here's the weight, it is applying the clockwise direction, right? So how much you applying the force? Let's see. Calculate the force that gender needs to export all the wheelbarrow leg of this one. How much your force needed? Calculate the force that the gardener needs to export to hold the wheelbarrow. How much force we require? Here, this force we are going to calculate how much force required for the gardener. So it's a R2 equals to 1.20 meter, and let's say F2 equals to watt, and F1 equals to how much is the weight? 400 Newton, and this is the distance is given here. R1 equals to 0.2 meters. So we can calculate F1 R1 equals to F2 R2, which is 0.2 into 400 equals to F2 into let's say calculate 80 divided by 1.2, which is equals to 66.66 Newton. Gardener requires the 66 newtons to pull the wheelbarrow from this stand. And next question is calculate the force exported by the ground on the leg of the wheelbarrow when the gardener is not holding the handle. Yes. So another thing is like instead of using the up, the gardener is there is a stand. So you calculate the same way you can use these techniques. So in this case, you don't have to consider from here to here is the distance. In second case, this is B. R2 equals to 0.5 meter and F2 equals to 1. And same way, 0.2 into 400 equals to 0.5 into F2 equals to 160 Newton. So that is interesting questions. Why in the second case this handle experience more force than the gardener? Why the gardener needs less force than the handle? The answer is gardener is a little far from the pivotal. More far will require the less force in order to balance. So and that's why the rotating effect will be more when you go further and further from your pivot.